Welcome back, everyone, to the solutions lecture for the logistic regression exercise project. Let's head over to the notebook and see what we can do. Okay, here we are at the exercise notebook. Let's go ahead and finish off the tasks. So the first thing wants you to import the libraries. Just go ahead and run that cell. We already filled it out for you. And then we'll also read in the data. So underneath the data folder, there was heart.csv. So we take a look at this. We have a bunch of features, and something you should check right away is to see if anything is a categorical feature that needs to be changed. But in general, it looks like everything that could be categorical, such as the sex of the person or patient, has already been either one-hot encoded or set up with an integer encoding. So for example, if we take a look at CP, it looks like it has some sort of integer encoding. Now we already mentioned there are sometimes drawbacks to integer encoding. For example, this would suggest an ordinal or ordering to the data. So we scroll back up here and see if that makes sense. So it looks like it's chest pain, and there's 4 different values for it. And if you check out the original source link, or if you check out the actual publication, you'll realize that there is an ordering to that chest pain. It's essentially lower chest pain, moderate chest pain, or severe chest pain, etc. And so that's okay to have it as integer encoding, since the ordering makes sense. So we'll go ahead and continue, and you can see we have a binary classification problem. DF target is unique, so you can go ahead and run that cell if you want. But now it's time to perform some exploratory data analysis and visualization. And as I always mention, feel free to explore the data further on your own in case you want to test out some more visualizations. The first thing we want to do here is just explore if the data set has any missing data points. And so there's lots of different ways we can do this. We could just say df_info and then quickly compare the amount of non-nulls here to the amount of total entries. And since these are all equal to 303, we actually right away can tell just from df_info that there is no missing information. The other way to check for this is you can say is null, and then recall that returns all these booleans, which we can then sum up, and it treats falses as 0. And you'll see quickly that all of them for every single feature is 0, meaning there's nothing missing, which is perfect for us. We don't need to deal with any missing data. Next, you can also check out the description of the dataset. You can say df describe in case you want to check out the various statistical properties for all the features. We'll go ahead and let you explore that. But let's move on to some visualizations. I want you to create a bar plot that shows the total counts per target value. And this is a plot type you should pretty much always do when you're dealing with classification, because right away it will tell you whether or not you're dealing with an imbalanced target. So we can do this by saying sns.countPlot. And I'm going to say that my x is equal to target, and my data is equal to df. You run that, and you'll see the following results. The next thing we want to do here is to create a pair plot. And you'll notice that we actually specified the columns you should do the pair plot for. In theory, we could just pass in the entire data frame for the pair plot, but the way Seaborn constructs the pair plot, you have to understand that it's actually doing a lot. It's creating a scatter plot for every single combination of features and the label. So running on pair plot on everything can take a really long time. It can also just present a large grid that really is not highly interpretable. So instead, we want to usually choose a couple of features as well as the target in order to perform the pair plot. An easy way to do this is by saying df.columns, and that reports back columns that you may be interested in. And so we mentioned we want you to do age and then cholesterol, as well as these other features and the target. You'll need the target if you want to color by hue. So I can copy these columns and then do something like this. We'll say SNS pair plot, and instead of passing in the entire data frame, which would take a really long time and produce just a visualization that's too large to actually interpret, we'll say df and then pass in the list of columns in brackets that we're interested in. Then after that, what we're going to do here is say that I want to set my hue equal to target. And that's the main reason we pass in target as one of our options. So really, we're just interested in 4 features and then coloring by target. And you'll find that for really large data sets, you'll be kind of whittling down things before you put them into the pair plot. So you run this, and you should get back, after a little bit of computation, the pair plot we just showed there. Okay, so we have this pair plot. Notice it's essentially the same thing as what we see here. The one thing you may have noticed is that since points are essentially stacked on top of each other, you may get some blue points stacked on top of orange points instead of orange points stacked on top of blue points. And that sometimes changes depending on what version of Seaborn you're using. If that is an issue for you and it becomes unclear, you can begin to add in alpha values to add in some transparency, or you can just start honing in and maybe doing things like a pair grid of customized hex plots or customized KDE plots in 2 dimensions, etc. So the fact that you can see the color difference looks quite different between 2 plots, as if you see more blue points here and more orange points here. It's actually the same data. It's just the fact that some points are on top of each other. You can see here that target 0 and target 1, 0 is still blue in both of these, but it looks like there's more blue points here. It's just the way they're stacked. So you may need to customize the plot further in case this is an issue for you. Now, in our case, we're not really too concerned about this. It doesn't look like there's any super clear relationship here. Some of these that look more circular may have kind of a linear relationship or positive relationship, but there's nothing that really stands out. Maybe the age, you can see here, the KDEs are quite different between them. But other things, like this feature right here, that one stands out a little bit too, but other ones kind of stacked right on top of each other. Okay, so usually a pair plot is kind of a good starting point, and then you'll hone in on what you're actually interested in. So then you could make a distribution plot of the ages and then hone in on that. We'll go ahead and move on though, and we'll say create a heat map that displays the correlation between all the columns. We already know how to do this. It's just simply SNS heat map. Do this a bunch of times, and we'll say df correlation. The one thing to note here is you should add in a color mapping if you want to get the same color mapping I have here. If you want the default, that's okay too. But you should also add an annotation of true, run the heat map, and you'll get something if you just do the defaults that's kind of too tiny, especially if you add in the annotation. If you take away the annotation, then you'll get something that can actually be kind of seen or read, but the colors are hard to identify. So you add in the annotation, but then you also need to enlarge the figure. So we'll say plt figure, fig size, and we'll say fig size is equal to, let's just say 12 by 8. Obviously, you can edit this as you please. You can also add DPI if you want to edit that further. So you can say DPI is equal to 200 to make it a little sharper. And there we go. We have a nice plot. In case you don't like this color mapping and you prefer the color mapping we had, we can say CMap and then say var this, and that will match the same color mapping. Okay, so I personally prefer this color mapping because you can see the correlations that kind of jump out either as super light. Obviously, there's the ones along the diagonal, but in this case, it looks like there's kind of heavy negative correlations here that immediately stand out. And recall, probably the most important correlations are the one here with the target. All right, so just a few don't seem to have any correlation. We'll go ahead and now move on to the machine learning part where we have to set up our data. So we're going to do a train test split. First, we need to separate out the features. And luckily for us, there wasn't any one-hot encoding to take care of, or integer encoding. It was essentially all done for you. Really, we're just going to focus on the logistic regression part. So we'll say df drop the target column along axis is equal to 1, and everything else is a feature. And then y is equal to the target column. Next, we'll perform a train test split. We'll go ahead and keep the test size as 10% with a random state of 101. So to do this, we say from scikit-learn.model_selection import the train test split, and then we'll also say from scikit-learn.preprocessing import a standard scaler. And then just as always, we call it train test split, and then quickly grab from the documentation the correct tuple. So we come down here, grab this, and then we'll edit it to match up what we show in the solutions notebook, which is a test size of 10%, so 0.1, and a random state of 101. So we'll set 101 there. Okay, run that. We did our train test split. Now it's time to scale the data. As always, we only train on or fit the standard scaler on the training data because we don't want any data leakage from the test set. Obviously, we've done this a bunch of times already. We simply create the scaler. So create an instance of standard scaler. And then the next thing we need to do is simply say something like scaled version of our xtrain data, or you can overwrite the xtrain data if you want to, is taking the scaler, and then we fit transform. You can do this in 1 step or 2 steps, up to you, on the original xtrain data, and then we'll also create our scaled version of the xtest data. Main thing to note here is that we're only transforming off xtest to prevent any data leakage or information leaking from the test set. Okay, so we have our scaled xtrain, fit transform and xtrain, transform xtest. Now it's time for the logistic regression model. Now, in the previous lecture series of multi-class classification, we showed you that you can separate out a logistic regression and grid search CV. Personally, that's the way I like to do it, but there is the option for the logistic regression CV. And to make sure that you have video of both the logistic regression and grid search CV approach, as well as the logistic regression CV built-in approach, we will go ahead and, for the sake of this project, use logistic regression CV. It's totally okay though if you decided to go logistic regression and grid search CV. That's probably the way I would normally do it, but we do want you to have some examples of using logistic regression CV that's built in. So to do this, we'll simply say from scikit-learn.linearModel import logistic regression CV. And if you're going to use logistic regression CV, I always recommend checking out the help on the actual class call or checking it out in the documentation. And essentially, CV is just going to explore the different C values for the penalty terms. You'll notice that by default, it uses a penalty of L2. Obviously, you could switch that out to be another penalty term. But in general, what it's going to do is search a grid of C's values. Now, what's kind of interesting here is instead of saying C is equal to something, it says CS, kind of a plural version of C. So if you notice, it says the default is 10. Now, that doesn't actually mean it's only searching the value 10 for C. In fact, if you provide C as an integer, then it's actually going to create a grid of C values, and they're chosen on a logarithmic scale. That is essentially the same thing we saw last time with grid search CV, where we created an np.log space. That is what logistic regression CV does automatically for you. So it tries to make this as convenient as possible. Essentially, you just need to pass in a single integer, and that's saying, okay, check out 10 possible C values on a logarithmic scale between these two numbers. So that's all being done for you. And in fact, 10 is a pretty reasonable amount of C's to check, so you could just leave it as the default. So let's see our performance with just that default. Obviously, you can check out more if you want, but we could just say that our log model is equal to an instance of logistic regression CV. And just by doing this, we are going to check out 10 different values for the penalty term, or the strength of the penalty term. So we have the log model there. Let's go ahead and fit the log model to our data. We'll say log model fit on scaled xtrain data against ytrain. You run that and you fit it. Obviously, for a really large data set and more values of C, this will take longer, but it's a pretty simple problem, and logistic regression is usually pretty quick to solve for. So here we have the fit done, and now what we can do is check out the C values. So you should be able to say log model dot, and if you hit tab here, you'll notice that it will actually report back the C's that it checked. So here are all the C values that it ended up checking, and if you want, you can remove that S to see the actual C value it decided on. So this is the C value that it had the best fit based off its cross-validation. You can see here that logistic regression CV is super easy to use. However, it's not as clear to the user or someone else reading your code what is actually being done behind the scenes. So that's definitely more clear when you personally set up your parameter grid with logistic regression and grid search CV. But with logistic regression CV in one call, this makes everything very easy to use. It's kind of a trade-off between how easy it is to interpret what's happening in the code versus how easy it is to actually execute and write out the code. So always a trade-off here when it comes to programming these things, but this is not so bad. Now what we're going to do is also we can explore the parameters. So we can say here log model get params, and this is actually a method call, so you have to put parentheses there, and it will report back the parameters that it was fitted on. So keep in mind that this is not the actual parameters of the coefficient it chose. These are the parameters of what you provided to the CV. So I said go ahead and check out 10 different possible C values. We'll go ahead and move on here to the coefficients, where we report back the model coefficients. That's really quite easy. We just simply say log model coef underscore, and it reports back the coefficients. If you did the exact same setup as we did in the solutions notebook, where you kept everything default for CV and you also kept the same random train test split, you should get the exact same coefficients or extremely close to those. So what we didn't show in any of the lecture notebooks for logistic regression, however, we have done something very similar for linear regression, is actually plotting out the coefficients. And this is really useful if you want to compare coefficients directly. It will kind of give you an idea of what are the important features and what are the not so important features. And especially when it comes to logistic regression, we know that those coefficients can be hard to interpret directly, but it's much easier to interpret them in regards to comparing the features themselves. So one coefficient can be compared to the other instead of just trying to isolate a coefficient in a vacuum and understanding what it means, because everything's being built off this logarithmic scale. Luckily for us, this is actually not so hard to set up, and you could reference the code that we've done before. The way I like to do this is to create a Pandas series of those coefficients where the index is equal to the columns of my features. Notice I'm saying x columns, not df, because I don't actually care about the target. And saying the index is columns allows me to have these feature names along the x-axis later on. And then we're going to say that the data itself is equal to log model dot coefficients. However, you'll notice that when we actually called the coefficients, it had two sets of brackets. We actually only need that first item. So we just need it in one set of brackets. Otherwise, Pandas series will complain. So we'll say here, pass in a 0. That's just to get rid of that extra bracket. So now that we have the coefficients as a series, I can check out coefs, run that, and I have this perfect little series that's ready to plot. Luckily, we can pass this into bar plot directly. So we can say sns.barplot and say x is equal to coefs.index and y is equal to coefficients.values. You run that and you should see a bar plot. However, you'll notice that it's actually not sorted. So probably what we want to do is sort the values first. So we'll also say right before this, coefs is equal to coefs sorts values. Run that. And now we have it sorted. And what we can do is edit this figure size. So right above the bar plot, I can say plt figure, fig size equal to something like 10 by 6. And if you want, you can also up the DPI and get yourself a nice looking plot. Whoops, I spelled fig size wrong. Let's fix that. There we go, fig size. And now we have this really nice sharp looking image. And obviously you could also edit the palette to change the color mapping here. Okay, so now what we're going to do is actually evaluate the performance of our model. So we have the model performance evaluation, and what we want to do is create a confusion matrix array, a confusion matrix plot, and our classification report. These are all really simple to do thanks to scikit-learn's built-in metrics functions. We'll say from sklearn.metrics, import the confusion matrix, the classification report, and you should be able to just tab autocomplete these. And then we'll also say plot confusion matrix. So we'll run those. And for all of these, all you need to do is get your predictions first. So we'll say ypred is equal to log model and predict off scaled x test data. And now that I have my predictions, I can say confusion matrix, pass in my predictions, and compare them against the test data. In fact, it's supposed to take y test first. There we go. Against our predictions, run that, and you get that result. And for plot confusion matrix, recall that you actually pass in the model directly, so you don't need the ypred. In fact, that kind of saves you an extra step. Later on, as you get more experience with scikit-learn, you may find yourself just skipping confusion matrix and going straight for plot confusion matrix because it's kind of saving you a step. Pass in your log model, pass in your scaled x test data, and then pass in your y test. It creates the predictions automatically for you, and you'll see that in general, you only had 5 mistakes out of this small training set. Not so bad. And of course, you can check out things like accuracy, precision, and recall, or you can just call the classification report to see it reported per class. So we can say classification report on ytest, ypred. And in general, this should be enough to give you an idea of your performance. So we can see here, not too bad, about 80%. Considering the benefit this could have for someone that we're able to detect heart disease based off some physical features, we're doing pretty good. If you tried to improve performance off of this, maybe something you could do would be a wider grid search. But given the data, it's kind of unlikely they'll be able to perform that much better since there's only 5 points you're really missing out on. So keep that in mind that if you just get one of these points correct, then you may see a huge jump in precision and recall when really it's just one person you're moving over. But depending on the context, one person could be a lot. Okay, finally, performance curves. Again, this is quite simple. Given the metrics library, we'll say from sklearn metrics, import, and we'll go ahead and just plot the precision recall. And we'll also plot the ROC curve. So go ahead and run those, and let's just plot them out. So we say plot precision recall curve, and we pass in pretty much the same thing we passed in here for plot confusion matrix, so we can just copy it. Log model, scaled x test, and y test. I'm going to put those in, run that. There's our precision recall, and you can see we're getting 0.97. And then we can also plot out the ROC curve, which is kind of the more common of the two. Go ahead and run that. and you'll see the ROC curve. Finally, let's go ahead and use our model on a quote-unquote brand new patient. So we're satisfied with our model, and a patient comes in with the following features. So now we want to actually ask, what does the model predict? So you have two options here. You could just use the model that we already have, because we're kind of treating this test data, because we already performed a grid search, as a holdout set. So if you want, you could retrain your model on all the data, or you can just use the model itself as is. Obviously, in the context of a real-world situation, you should probably retrain your model on all data, because this is essentially the same thing as deploying your model. But just to save a little bit of time, I won't retrain on everything, but obviously in a real-world situation, it's not a big deal to retrain your model. So we have this patient set up for you, and what we're going to do is quite easy. We simply say the following. We say, okay, I want my log model to predict on this patient. And you'll notice that there's two sets of brackets, because that's essentially the formatting and shape that log model expects, because it was trained on two-dimensional data. So if you run log model predict, it should predict a 0 class, and it should be really sure about this. So you should be able to also predict the probabilities for this. Run that, and it should almost be like 99.99% sure this person belongs in the 0 class. Notice how small a number of probability, almost 0 probability, that it belongs to the 1 class. All right, and that's pretty much it. Again, kind of in a real world situation, before you would run this final prediction, you'd retrain your model on all the data. That's it, and I'll see you at the next section.